Okay, Chapter 3, Section 2, Derivatives of Exponentials and Logarithmic Functions. Okay, in order to achieve this goal of figuring out what is the derivative of an exponential function and a logarithmic function, let's first step back and revisit a family of functions called exponential functions. Recall that if we have a function of the form f of x equals to b to the power of x, where b is allowed to be a value somewhere between 0 and 1, not including 0, not including 1, or b is allowed to be a number strictly greater than 1. Right? Another way of saying this is that b is a member of the set from 0 to 1 unioned with 1 to infinity. Okay, so it's allowed to be anything except not 0 and not positive 1. Any positive number, we don't include 0, we don't include 1. Okay, what do these look like? So for example, this is just the general form. This is in general exponential functions. But as examples of exponential functions, we could have g of x equals to 2 to the x power. That's one example. If we wanted some values, of course, we can create a table. Here's x, here's g of x. If x is equal to 0, then we get a 2 to the 0 power, which is 1. If x is 1, we get 2 to the first, which is 2. If x is 2, then we get 2 to the second, which is 4. Okay, so we start to see powers of 2. So 3, we get 2 to the third power, which is 8. X is allowed to be a negative number, so we could have negative 4, for example. That would be 2 to the negative 4 power, which is equal to 1 over 2 to the positive 4 power, which is equal to 1 over 16. Okay, and we can keep going that way. Another example could be that maybe, well, let's not use h. How about w? W of x equals to 3 to the x power. And again, we could create a little table. Here are x and w of x values. When x is 0, we get 3 to the 0, which is 1. Okay, that's something to note. Whenever we raise anything to the 0 power, we get 1. We can let x be 1. We get 3 to the first power. That's 3. We can let x be 2. That's going to be 3 to the second power. That's 9. Okay, so we start to see that these are powers of 3. Also, x is allowed to be negative, so maybe it's equal to negative 3. That would be 3 to the negative 3, which is equal to 1 over 3 to the positive 3 power, which is equal to 1 over 27. Okay, and so, of course, b is a variable that can represent any constant. In this case, we let b equal to 2. Here, we let b equal to 3. Here, we let b equal to 3. But of course, it could be anything, as long as it satisfies these two conditions, right? So the only thing we're not really going to consider is the case when b equals to 1, because, well, then that just gives you a really boring case. If we do some function y equals to 1 to the x power, 1 raised to any power is 1, so the whole thing is just equal to 1. There's nothing wrong with this mathematically, it's just boring. Too boring. Too boring. And we can't let b equal to 0, because then we'd have 0 to the power of x, and most of the time that's going to be fine. So if we let b equal to 0, then we could have a function like y equals to 0 to the x power, and most of the time that's going to be boring as well. 0 to the second power is 0. 0 to the fourth power is 0. But we might have some weird things, like what if x is 0? We'd have 0 to the power of 0. We've never really explored that. And if x is negative, then like 0 to the power of negative 2, to get rid of the negative, we move it underneath, right? So we could have 0 to the second power, no problem, that's 0. We could have 0 to the power of 0. That's just weird. We never really thought about that. We could have y equals to 0 to the negative 2 power, which would make it 1 over 0 squared, which would then be undefined. Undefined. That's strange, right? So for that reason, we don't consider this, right? Too complicated. In more advanced classes, you can think about that, but for us, We're not going to worry about that. Likewise, if we let b equal to a negative number, we could run into weird things as well. So for example, think about b equals to -2, for example. We could have the equation y equals to -2 to the power of x. And for some values, the output will be negative. So like, for example, y equals to -2 to the power of 1. Well, that's just going to be -2. And if we let x equal to 2, let's make it 4. Now, if x equals to 2, we get -2 to the power of 2. Now we get a positive 4. So sometimes we get a negative, sometimes we get a positive. And what if it's a fractional value like 1/2? We get y equals to -2 to the power of 1/2. Well, that's the same thing as the square root of -2. Now we get an imaginary. Now we get an imaginary solution. Okay, so sometimes the outputs will be negative, sometimes positive, sometimes imaginary. Too complicated. So, too complicated. That's fun for another math class. For us, we ignore all that, right? We're just focusing on the cases where b is allowed to be a value between 0 and 1, not including 0, not including 1, or a value that's strictly greater than 1. In all of those cases, we consider functions that fit that form. Okay, what do these graphs look like? So let's take a look at these graphs. Okay, so here in blue, I have 2 to the power of x, and this is the general shape. I can zoom out and see what happens. So as x goes toward -infinity, the function gets infinitely close to 0. It has a horizontal asymptote at the x-axis. And as x goes toward +infinity, the function gets infinitely large in the positive direction. Okay, and then here is the graph of 3 to the x power. It has the exact same shape. As x goes toward -infinity, the output will converge towards 0, gets infinitely close to the x-axis. It has a horizontal asymptote there. And as x goes out to +infinity, it shoots up toward infinity, and in fact, it'll grow there even faster, as we can see here. Okay, so in general, the family of exponential functions have this shape. So for example, let's say we had okay, so now I've written it into Desmos to give me a general function. So here's b to the x power where I have this slider. Currently it's at 2, but we see that that's the graph, that orange one. And as I slide this around, we see that it keeps that same shape. Okay, so here is the general graph of b to the x, where b is this variable that I get to slide around. Currently it's at 2, so this is the graph 2 to the x, just like we had before when it was that blue one, 2 to the x power. Notice that 2 to the x and 3 to the x both go through the point 0, 1. So 2 to the 0 is 1, 3 to the 0 is 1. And as x grows toward +infinity, both graphs go toward +infinity. As x grows toward -infinity, both graphs grow toward the x-axis. So now if we leave it in general, we see that this is generally what happens. We have that general shape whenever b is greater than 1, right? So this is what they look like. Let me zoom out. Even that one, it looks like a line, but it's not. If I zoom out, zoom out, zoom out, then it starts to look more like the same shape. Okay, so as long as b is strictly bigger than 1, then this is going to be the general shape of our graph. Okay, zoom in again. Okay, on the other hand, if b is a value between 0 and 1, then this is the general shape we're going to have. It's kind of a reflection, a mirror image about the y-axis. That's when it's between 0 and 1. Okay, let me zoom out a little bit more. This is what you get. Remember, b is not allowed to be 0, it's not allowed to be 1, it's not allowed to be a negative. But if it's a fractional value between 0 and 1, then it'll have this shape. Notice that it still goes through the point 0, 1, right? 0.7 to the power of 0 is still 1. Okay, so they always go through that point. Let's just move it around now. Let's just say it flips between that and 10. And so we can see what happens to our graph. As long as the value of b is between 0 and 1, it'll have this sort of shape. As it gets closer and closer and closer to 1, expands out. Let me zoom out a little bit more. As it gets closer and closer to 1, it comes that way, and then at 1 it's just a horizontal, flat, boring line. We ignore that. That's why we avoid using that. Plus, it's the only one that doesn't fit the general pattern of the rest. This one is a horizontal line. And then past 1, it begins to have that same shape again. Okay, so just let it play. It's got that shape, and then it flips to the other side. Okay, well, enough fun with that. What we want to do is think about the general b to the x power function. Let's zoom in here. Let's get a nice pretty one. Well, in fact, let's just work with 2 to the x. There it is. Okay, so we want to find the derivative of the function b to the x in general. Without loss of generality, we know that I could just draw it like this, and you would know that it represents one of these graphs. Okay, so without loss of generality, let's just assume that this represents the graph of some function f of x equals to b to the x. We just saw that, in fact, it might be a little bit different because, it might have a slightly different shape depending on the value of b, or it might have, might face the other way. But that's okay. This is just to give us something to reference, something to look at. But we have to know that, in fact, it might look a little bit different based on the value of b. But just in general, without loss of reference, without loss of generality here, we're just going to pick this one to be the shape, just to lock onto a picture. Okay, so let's say that I'm interested right here at x equals to a, right here. And I want to find the derivative of the function at this point. Okay, so then let's say that this red line here represents the line tangent at this point. So that means that this point right there would be the point a comma f of a. Well, okay, f of a in this case would be b to the a power. Okay, and so we're interested in the slope of this line, right? The slope of this line is the derivative. Okay, so let's use our limit definition of a derivative to find f prime at a at this point. So we're going to use this equation. We're going to say that f. Okay, so from our limit definition of derivatives, f prime at a, at point a, is going to be equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. Now the f of x function is in fact b to the x power. So let's highlight that. So that's the rules we're going to follow. So f of a plus h becomes b to the power of. Okay, and so now we get to use an interesting property of exponential functions. Remember that if we have 2 to the power of 3 plus 5, that's equal to 2 to the power of 3 times 2 to the power of 5. Or backwards, if we're multiplying two exponential numbers with the same base, we add the exponents. Okay, so here we have an addition in the exponents, so we get to separate it. Okay, and so now after we've done that, we can identify that this and this are like terms. We can factor that out. Okay, so all I did is I factored out b to the power of a in the numerator, leaving me this. B to the power a times b to the h minus 1 all over h. Okay, so now with our work with limits, we also know that if there's some function or constant that has nothing to do with the variable in our limit here, in this case h, then we can pull it out, right? So in terms of this limit, h, the variable of the limit is h, so we can put that out in front and rewrite it this way. F prime of a is then equal to b, the power of a, times the limit as h approaches to 0 of what this thing that's left over. This is going to be b to the h power minus 1 all over h. Okay, now what in the world is that? Well, let me rewrite it just a little bit more and say that I'm going to rewrite it this way. F prime of a equals to b to the a power times the limit as h approaches to 0 of b to the, I'm going to insert this in here as 0 plus h. We're allowed to do that, right? You can always add 0 to anything. Doesn't mean anything. H plus 0 is the same thing as h. Okay, minus, and then instead of a 1, I'm going to rewrite it as b to the 0. B to the 0 power. All over h. Okay, and this is where b to the h power, same thing as b to the 0 plus h, minus, and then b to the 0 power, still going to be 1, and keeping in mind that b is a value between 0 and 1, or greater than 1, so we don't really get into anything weird by raising it to the power of 0. This is always going to be 1, so this is equivalent to this. Now, why would I write it this way? Note that this is, in fact, the derivative of our function, the definition of the derivative of our function evaluated at 0. So this then becomes f prime of a equals to b to the a power times, and this is f prime of 0. Right, let's look at our definition of a derivative. If I come back over here, f prime at a, and I replace all of these values, let's say I want to replace this a with a 0, this a with a 0, this a with a 0. If I replace all of those values with zeros, 0, 0, and 0, I would get exactly this, b to the 0 plus h minus b to the 0 all over h. So this whole thing is the derivative evaluated at 0. Okay. All right, so let me just flip these two around and let's figure out what we have here. F prime of a equals to f prime of 0 times b to the a. Okay, so what is this saying? This is saying that if I want to find the derivative of the function of the exponential function b to the x power at x equals to a, that derivative is equal to the function itself evaluated at a, b to the a, times the derivative of the function evaluated at 0. Okay, so a is going to be movable. We're going to want different values of a, right? Like when a is a 7, when a is a 2, when a is a 2.5, right? So that's going to be movable. But 0 is going to be, the value of f prime of 0 is going to be a constant. So let's put it into our graph here. So at 0, then this is going to be 0, 1. It's going to be that point right there. And then the slope of this line, slope of tangent line, at point 0, 1, well, that's going to be f prime of 0. Well, okay, we don't know what that is. It depends on the actual value of the function. But the interesting thing is that it's going to be some constant, right? Once you figure it out, you only have to figure it out once. And once you figure out what that is, then in order to find the derivative of any value in that function, the slope of any line tangent to our function, it's equal to the actual value output of that function at the value a times a constant, which is equal to the derivative of that function at 0. I know, mind blown. Okay, so to recap what this means one last time is that if we are given some function in the form of b to the x power, so it's in the family of exponential functions, and we want to find the derivative at x equals to a, right? In our picture here, we want to find the slope of this tangent line, where this is some value a in the domain of our function. Then according to our work, what we have found is that the derivative at a, so the slope of this line over here, that slope, is equal to the value of our function f evaluated at a, right? This is f of a, just putting an a there, times the derivative of the function evaluated at 0. Whatever the slope of the tangent line at 0, whatever that slope value is, times the value of the function evaluated at a. Okay, so let's do a couple of classic examples and see if we can get a better handle of what this means. Okay, so what we've established is that if some function f of x is equal to b to the x power, where b is a member of the set between 0 and 1, union 1 to infinity. So if this is the case, we have something that fits this form, then the derivative at a, when x equals to a, then the derivative f prime at a is equal to f prime of 0 times b to the a power, right? That's what we just found. Or another way to put this is that f prime of a is equal to f prime of 0 times f of a, the original function evaluated at a times this derivative evaluated at 0. Okay, so now let's take two, this is very general. Let's take two very, very common cases. Let's look at the case where b equals to 2 and when b equals to 3. So again, without loss of generality here, we can just say this is the graph of, let's say this is the graph of g of x equals to 2 to the x power. And we'll call this one over here w of x equals to 3 to the x power over there. And there is some value here. Here is a. So we're coming up here and we're going to draw the tangent line. So let's say that this point here is the point a, comma, 2 to the a power. And so, of course, we're interested in the slope of this line, which would be the derivative evaluated at a. Same thing over here. If this is some other point over here, just without loss of generality here, let's say that this is the point a. So therefore, this would be the point a, comma, 3 to the a power. That. Okay, so if I have g of x equals to 2 to the x power, according to this formula, I need to figure out what is this. So this would be g prime at a. The derivative at a would be equal to the derivative, its derivative evaluated at 0, times 2 to the a power. Okay. Likewise, over here, this would be w of x equals to 3 to the x power. So the derivative evaluated at a would be equal to the derivative of w at 0 times 3 to the a power. Okay, so in both cases, we need to figure out the slope of the line tangent to our function at x equals to 0. So if we look at the line tangent at the point 0, comma 1 on this function, and same over here, this is the point 0, comma 1, we need to find the slope of this line, right? That would be slope of this line is w prime evaluated at 0, right? It's the slope of the tangent line at that point is the derivative evaluated at 0. And the slope of this line, slope, would be equal to g prime of 0. Okay, so now we got to figure out what that is. So let's figure that out like right in here. What is g prime of 0? Well, we have our definition. This is going to be equal to the limit as h goes to 0 of f of 0 plus h minus, oh, not f, g. G valued at 0 minus g of 0 all over h, which in our little case would be equal to the limit at h goes to 0 of 2 to the power of 0 plus h minus 2 to the 0 divided by h. Now 0 plus h, well, that's just going to be h, and 2 to the 0, well, that's just going to be 1. So this simplifies. This will simplify as equals to the limit as h goes to 0 of 2 to the h power minus 1 all over h. G prime of 0, g prime of 0. Okay, now how can we figure out what that is? Well, let's just use our calculator. We can figure it out by the table function in our calculator to figure out what this limit is. Right? There's no other simple trick for us. We can't really factor our way out of this. We can't really use any of other algebraic tricks that worked before. So if we have nothing else to go by, let's just punch this into our calculator and see what happens as I input values that are closer and closer and closer to 0. Do we see a pattern for this? Does it blow out of control and go toward positive infinity or negative infinity, or does it walk towards some number, get infinitely close to some number? Let's figure out what that is. So let's go to our calculator. Now remember, our calculator doesn't like to do h, so we'll have to do 2 to the x power minus 1, close parentheses, divided by x. That's exactly this equation, except I replaced everything with an x, because our calculator doesn't like to do anything in h. Okay, so now that we type that in there, make sure that there's no other equations, and we're going to go over our table. So make sure you hit table set, and that the independent variable is under ask, the dependent is under auto. Let's go to our table, and then delete anything that was already there. And let's just do one really easy one for calculation's sake. So if we put a 1 there, we're going to get a 1. Does that make sense? So if we put a 1 here, 2 to the 1 power is 2, minus 1, that's 1, over 1, which equals 1. Okay, so that makes sense. All right, now we want to walk towards 0, get infinitely close to 0 from both sides of 0. So we can figure out what this limit is, if anything at all. Okay, so let's make it 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.2, 0.1. Okay, there seems to be a nice pattern. It's getting smaller and smaller and smaller, and it's growing towards something close to 0.7. How about 0.01? Now we're getting really close. Okay, now 0.69. Okay, now let me walk back up here. Unfortunately, I don't think it's going to let me do any more. It starts to replace them after that. So I wish I could scroll down. So let's just start from up here. How about 0.2, 0.1, 0.01, 0.001, 0.00001. Okay, so it starts to get really, really close to 0, but I've always done positives so far. We'll look at negatives in a second. And it looks like this thing is getting really close to this decimal, 0.6931. Let's see what happens from the other direction. Does it make a difference? So let me change some of these values. How about if I start down here at -1? Oops, go to problem with -1. Clear. -1. Okay. -0.5. Okay. How about -0.2? About -0.01? About -0.001? About -0.000001? Okay, you can see from here that they seem to be growing really, really close to positive 0.6929 or 3, somewhere around there. Let's just round it to 693. 693. They seem to be heading that way from both directions. Okay, so it's not a mathematical proof, but hopefully we feel confident that this is where they are heading. The limit is going that way. So let's just leave it at rounded to 0.693. G prime of 0 equals to 0.693. Okay, remember we can interpret this as about 69%. Okay, so now that we're armed with that, that means that this constant here is this decimal. So the derivative evaluated at a is equal to 0.693 times 2 to the a power. Right? And like I said, one way to interpret this decimal is to think of it as a percentage. It's 69% of this number. So if you want to find the derivative at a, find the output of our function at a, and then the slope of the line tangent is 69% of that value. Right? It's a constant proportion of the height of our of the output of our function. Right? So for example, if I wanted to find when a equals to 3, and I wanted to find the derivative of this function at 3, then it's going to be equal to 0.693 times 2 to the third power. So this is going to be 8 times 0.693. To the power of 3, which is equal to 8, times 0.693, 5.544. Okay, so just based on this really easy formula, it's letting me know that when the input value is 3 to this function, right, if I make this equal to 3, then its output would be equal to 2 to the power of 3, which is equal to 8. So the output would be 8. So therefore, this point right there would be the point would be the point 3, 8, and then the derivative at that point would be equal to 5.544. That would be the slope. Slope of that line would be 5.544. Just following this simple formula. Right? Okay, let's do the same thing for this case now. So w prime of 0 is equal to the limit as h goes to 0 of w 0 plus h minus w of 0 all over h. So w prime of 0 is equal to the limit as h goes to 0 of 3 to the power of 0 plus h minus 3 to the 0. So I'm really just copying this exact same work here, except here w of x is equal to 3 to the power of x instead of 2 to the power of x. And so all of this gets divided by h. Again, 3 to the 0 is 1, and we can simplify this to 3 to the h power. So this is the limit as h goes to 0 of 3 to the h minus 1 all over h. And again, we can use our calculator's table function to figure out what this is. Very similar to that, except instead of a 2 to the h minus 1, we get a 3 to the h minus 1. Okay, so let's go figure out what that is in our calculator. So we can figure out what this constant is. Okay, so now let's go back to our equation, and let's just come back over here and change this from a 2 to a 3. Everything else stays the same. Enter. 3 to the x minus 1 all over x. And let's go back to our table. And again, we're interested in approaching 0, so we can already see some values here. As these input values got closer and closer to 0 from the positive side, it's like the output values were getting really close to 1.099. And if we approach 0 from the left-hand side, -1, -1/2, -0.2, we see that the output values were also approaching the same number. So somewhere around here, they're approaching something really close to this number. Let's round to 4 decimal places. So 0.986, 189.86, 0.986. So approximately 1.0986. Okay, so then going back to this formula then, the derivative of a is equal to this constant number, 1.0986 times 3 to the a power, right? Where this is just some constant times that. Okay, so again, just to put some context into this, what if we wanted to find the derivative when a was equal to 4? Let's put it in green. If a equals to 4, find w prime at 4. Okay, so coming up to here, we're saying, okay, what if this is a 4, which means that this is really the point 4 comma 3 to the 4th power, right, which means it's really equal to 4 comma 81. 3 to the 4th power is 81. And so we want to find this slope right there. So that slope right there is going to be equal to, so f prime of 4 is going to be equal to 1.0986 times 3 to the 4th power. The output of the function, so the height of our function, is part of the equation for figuring out the slope. It's in fact, we can also think of this as a percentage. This is 109% of the output value of our function. So we can multiply 1.0986 times 81, and that'll be the slope of the line tangent at the point 4 comma 81. So w comma 4 equals to, let's get our calculator. So 1.0986 times 81. There. The slope at that point is going to be 88.9866. Okay, so the slope here, which is equal to the derivative, is going to be equal to 88.9866. Okay, let's recap what we've done. It's getting really dense in here, right? So if we have a function of the form b to the x power, that's a general way of stating all exponential functions, where b is allowed to be a value between 0 and 1 or between 1 and infinity. and we wanted to find the derivative. We found that the derivative at x equals to a, for some value a, the derivative is going to be equal to evaluating your function back at a times a constant, where that constant is the slope of the line tangent evaluated at 0, or f prime of 0. So we can state all that in one of these two ways. F prime of a equals to f prime at 0 times b of a. B to the power of a. Or we can also restate it this way, that the derivative evaluated at a is equal to the derivative evaluated at 0 times f of a. Okay, so very interesting. This is the only function that we know that does this. Its derivative is going to be equal to the value of the function times some constant. And that constant varies based on the value of b. So when b equals to 2, so if we wanted to find a more specific example, this is a very general statement, but now we came over here and said, well, let's think about a very specific case. What if b was equal to 2? So let's say that this is the graph of 2 to the x power, and we wanted to find the derivative at a. Okay, well, according to this little formula, it's equal to this. G prime of a equals to g prime of 0 times 2 to the a power. So we just have to figure out what this g of 0 is. Well, by the limit definition, we can rewrite it this way, and we get to this point. And once we get to this point, well, we can just use our calculator to find it from there. So this was our calculator. The calculator helped us get through this. There is a way to do it without your calculator, but we will revisit that down the road. We need a little bit more math to be able to do it without the calculator. But for now, it's good enough. So we use our calculator. We figure out that g prime of 0 equals to this number, and that's that constant there. So if we want to find the derivative of g of x equals to 2 to the x power at x equals to a, its derivative is going to be g prime of a equals to this constant times 2 to the a power. Okay, so if a equals to 3, and we want to find the derivative when a equals to 3, then we have to figure out the output of the function times some constant, and that's this constant here. Okay, so we can also think of it this way. 0.693 can be thought of as a percentage. It's approximately 69%. So the derivative at 3 is 69% of the value of the function evaluated at 3. Right? That's another way of thinking about it. G prime at 3 is 69.3% of the value of g of 3. Evaluate your function at 3 and do 69% of that value, and that's your derivative. The slope of the line tangent at that point is equal to that. That's very interesting. And this number stays constant for all of the function 2 to the x for any value of a. Good. Okay, then just to contrast it, I did another one over here with 3 to the x power. Okay, so then according to this little formula, then this would be the derivative. G prime of a equals to w prime at 0 times 3 to the a power. Again, this is going to be some number, some constant. We can use our definition of derivatives, the limit definition of derivatives, to give us this. And again, we use our calculator once we get to this stage. Once we get to this point here, we can use our calculator to approximate it. Later on, in a couple more sections, we'll be able to do it without that. But for now, we need our calculator. So we use our calculator, good enough for now. We get to this decimal. So that becomes this. So for the function 3 to the x, this is always the constant. Okay? So if a was equal to 3, and you're like, okay, what's the derivative of this function 3 to the x when the input is 4? Okay? So when it's equal to 4, all we have to do is find the value of 3 to the 4th power, which is 81, times this constant. We can think of this as a percentage, and it's about 109%. It's 109% of that value. Okay? Again, exponential functions have this very special property. When you want to find the derivative, it's equal to the value of the function times some constant. some percentage of it. So another way to look at this one is to say that this is g prime of 4 is 109.86% of w at 4. Figure out the actual output of our function at 4 and multiply times this percentage. Okay, so that's going to be the general rule that exists for any function that fits the form b to the x. Okay, let's come back up to the work we did earlier when we were finding the derivative of the exponential function b to the x in general. And we got to this stage here as we did the limit definition of a derivative, and we got to this stage here. And then I changed it a little bit, manipulated a little bit, so that we can see that this is actually the definition of derivative evaluated at 0. So that's how we were to get that. It's f prime evaluated at 0. Okay, well, when we had the case of b equals to 2, when b equals to 2, we found out that this whole part here, this whole thing equal to a decimal. The limit, so when b equal to 0, this portion, according to our calculator, equal to 0.693. Therefore, we had that f prime of a is equal to 2 to the a power times this decimal, 0.693. Okay, well, in the case when b was equal to 3, then we had that the limit as h goes to 0 of 3 to the h minus 1 all over h was equal to 1.0986. Therefore, the derivative f prime of a in this case would be equal to 3 to the a power times this decimal, 1.0986. Okay, so every time we pick a new value of b, then the slope tangent at 0, this part of it, is going to be some other different constant number. So the natural question is, well, is there going to be some value of b such that this whole portion equals to 1? Right? So that's what we wanted to find out. We want to find a value of b such that this limit as h goes to 0 of b to the h power minus 1 all over h, that this whole thing just equals to 1. Good. And if it equals to 1, then that means that the derivative at that value of b, f prime of a, is going to be equal to b to the power of a times 1, right? Where b to the power of a, well, that's just the original function evaluated at a. So for that very special value of b, we will have that f prime of a is going to be equal to f of a. Okay, so b is the value. This will happen when b equals to e. B equals to e is in fact the number that we want. Okay, so we kind of reversed engineered it. We were looking for a number that makes this work, and we found it to be approximately 2.718. It makes sense that it's somewhere between 2 and 3. So 2.718 is the number that does that. Okay, all right, let me write that down. So again, in general, if we have f of x equals to b to the x power, we know its derivative at a is going to be equal to b evaluated at a times f prime of 0, right? That's just in general. But now, if b equals to this number e, which is approximately 2.718, then that means that our function, let's leave it in f, that means that f of x is now equal to e to the x power, and its derivative at a, prime of a, is going to be equal to e to the a power times f prime of 0, and e is going to be exactly the number needed for this to be equal to 1. So for us, this is equal to the limit as h goes to 0 of e to the power of 0 plus h minus e to the 0 all over h, which simplifies to the limit as h goes to 0 of e to the h minus 1 over h. And we know that this is exactly equal to 1. Okay, that's by definition. That's how we know it, I should say. There's very few things in math that are created. There's a real discussion whether math is invented or discovered. So I don't know if you want to say that we created this number e to fit this form here, or if we discovered it. I don't know what the right language would be, but it was chosen for that reason. Whether it was discovered or created, it was chosen to be the number that makes this true. And if it makes that true, then we have this, that the derivative evaluated at 0 equals to 1. And so therefore, this whole portion is just a 1. So f prime at a equals to e to the a power. And e to the a power, well, that's just equal to the original function evaluated at a. So f prime of a equals to f of a. So this is saying that the derivative of the function at a is equal to the value of the function at a. Right? What would that look like in terms of the picture? So let's say we have, let me just do a rough sketch here. We have some exponential function that looks like that. Let's say that this is e to the x power, and then I want to find out what is the slope of the line tangent. Okay, let's pretend that's tangent there. What's this slope here? Slope, I'm interested in that slope. And let's say I wanted to find out here. What is this? This is 2. Okay, so if it's 2, that means that its height is e squared, right? This is the e to the x power, this is e squared. I can just figure that out with our calculator. And what's the slope going to be? Well, it's going to be equal to e squared. This is the only function where the output of the function is equal to the slope of the line. Okay. Could be a fractional value as well. Let's say we had that, and that's equal to let's say that's equal to 1/2. Then this output would be e to the 1/2 power, also known as the square root of e. You're like, okay, and then what's the slope of the line tangent at that point? Well, the slope is also equal to the output of the function. The slope is still equal to square root of e. Okay, so that's what's interesting about this, this function, e to the x power. So another way to rewrite this then is this. Given f of x equals to e to the x, f prime of x equals to e to the x, right? It doesn't change. It's just the value of the function. The derivative of the function is equal to the same thing that you would get if you evaluate the function. Or likewise, we could say that the derivative with respect to x of e to the x equals to e to the x, right? The derivative of the function e to the x equals to e to the x. The only function that can do this. Okay, very important function, and that's why e is such an important number in calculus. Okay, note that this doesn't follow the power rule like before. That's a very common mistake. Remember that for the power rule, we had cases like this, x to the power of 3, and we wanted to find the derivative with respect to x of this. So remember, the power rule says to bring that 3 out in front, 3, x to the power of 3 minus 1. So So we'd get 3x squared, right? That is not this. This is different. Notice that here the x is the base of the exponential number, whereas here the x is in the exponent, right? The base is a constant, it's a 3. So it doesn't follow this rule. So a very common mistake is for people to say this, that the derivative with respect to x of e to the x equals to x e to the x minus 1, right? Bring that x out in front and subtract 1, and that is not true, right? That's not how it works. The derivative of e to the x is the easiest thing we could do. It's just equal to e to the x. So this whole long drawn out thing has been just to convince you that the derivative of e to the x equals to e to the x. You're welcome. Okay. All right. Let's do some. Let's look at what it looks like on Desmos. So here we have a variety of exponential functions. That's 2 to the x there. Here is 3 to the x. So now let's graph. And then if we had b to the x power, I can move b around. I can see that it has these kinds of different shapes. Okay, so now let's say that I just land on a specific one. So let's get rid of that. Let's just say that this is e to the power of x. It'll look like that. It makes sense because remember, e is approximately 2.718, so it's going to be somewhere between 2 and 3, closer to 3 than it is to 2. But okay, so it's this orange one here. Let me get rid of the other ones for now. Okay, so here it is. That's e to the x power. And if I want to find derivatives, let's visualize the derivatives. Okay, so the orange one is e to the x, and here's this red line that's our derivative function. We've seen this many times before. Hopefully we're comfortable with it. So when we say the derivative, we're looking for the slope of the line tangent, right? So I want the slope of this red one as it goes across, goes around it. Okay, so let me have Desmos here just provide us the answer. Here it is. So right now, when the input is, let's make it a nice whole number. When the input is 1, the output is 2.718. That's approximately e. Okay, so when the input is 1, the output is e. And what's the slope of that red line? Well, here it is. Here's the slope, and it's e. Okay, it gives the same output. The output of our function, the height of our function, is equal to the slope of the line tangent. Let's do another one. Let's do another whole number. How about just 2? When the input is 2, the output of our function is 7.389. That's kind of this altitude here. And what's the slope of the line tangent at that point? It's going to be the exact same answer, 7.389. Okay, so this is a unique function where the output of the function, the y value of our function, is exactly equal to the slope of the line tangent to the function at that point. Okay, that's what makes this number special. It's the only one that does that. Good. Okay, let's look at some examples. Okay, find the derivative of this function, f of x equals to 3 e to the x plus 7x cubed minus 6x squared plus 9. So to find the derivative, that would be f prime of x is equal to the derivative with respect to x of all of this, which would be 3 e to the x plus 7x cubed minus 6x squared plus 9. So f prime of... Okay, so we know we can separate these, so this will become the derivative with respect to x of 3 e to the x plus the derivative with respect to x of 7 x cubed minus the derivative with respect to x of 6x squared plus the derivative with respect to x of 9. Okay, we know we can pull a constant out. F prime of x equals to 3 times the derivative with respect to x of e to the x plus 7, derivative with respect to x of x to the third, minus 6, the derivative with respect to x of x squared. And the derivative of a constant is just 0. So I know that this is just going to be 0, derivative of a constant. Okay, so now we just discovered the derivative with respect to x of e to the x is equal to e to the x. So this is going to be 3 e to the x plus 7 times, and now we use our power rule. This becomes 3 times x to the 3 minus 1 minus 6 times, and this becomes 2 times x to the 2 minus 1. Okay. So f prime of x equals to 3e to the x power plus 21x squared minus 12x to the power of 1. Okay, and that's our final answer. Okay, so now we gotta come back and remember some more stuff from our prerequisite class. So hopefully you did a lot of good work back then with exponential functions and logarithms. So we're really well aware that they're inverse functions of each other. So here's some nice stuff to remember. So in logarithmic form, we could have something written as y equals to log base b of x, and then that is equivalent to rewriting it as x equals to b to the y power. When I teach this, I like to really focus on here, right? So in this notation here, focus on the b, and we know that it is being raised to the power of y. So b raised to the power of y must be equal to x, right? We get this little circle that happens. B to the y power must be x. So b to the y power equals to x. Okay, when it's written in exponential form like this, we just finished talking about what those things look like, what those graphs look like. So when b is greater than 1, we know it has this sort of a shape. And if we think about log base b of x, its inverse operation, we're really just flip-flopping the input-output terms. So we end up getting something that's a mirror image across the line y equals to x. Okay, so now on the other hand, if y equals to b to the x and b is a value between 0 and 1, it's going to look a little bit different. But the same property remains, that the log function, the inverse log function, is going to be, the log function, which is the inverse function of the exponential, is going to be the mirror image graphed across the line y equals to x. Okay, so b is allowed to be any number between 0 and 1 or 1 and infinity. The domain of the exponential number is all real numbers, and its range is all positive numbers, right, not including 0. And then the reverse is true for the log function then. Okay, so hopefully all this looks familiar. I know that if you didn't have a good solid background and then everything I just said was gibberish. So go back and look at it. You can look at my videos. I think it's like chapter 4. I'm not really sure where it is. If you flip around through the videos in my pre-calculus class, there'll be a video that I do a whole long extended thing about exponential numbers. Okay, so you're welcome to go check that out. Okay, so then of all the values of b that we could do, the two most popular ones are 10 and e. For two reasons. Of course, 10 is very popular because we have a base 10 number system. So things work out really nicely with 10 very often. So it's a very common base to use. And as we just saw, e is very important as well. So it becomes a very popular base to use as well. Okay, so popular, in fact, that we gave it a different notation. Log base e of x is otherwise known as ln of x. And log base 10 of x, well, that's just log of x, right? Just sort of by default, if there's nothing written there, then we know it's a 10. But normally we like to write it, even if it's a 10, Well, I like to write it even if it's a 10, but not everyone. Okay, so hopefully this looks pretty familiar and we're ready to move on. Let's try and find the derivative of the ln function. Okay, so let's say, okay, so now let's say we're given f of x equals to ln of x. Find the derivative at a. Okay, so let's set up our limit definition of derivatives. Okay, and so now the function is ln of x, so this would be ln of a plus h minus ln of a all over h. And here we would like to use a property of logs. So let me remind you that one important property of logs is that um, ln of a minus ln of b equals ln of a divided by b. Okay, so a difference of two log functions with the same index, so ln of a minus ln of b equals to ln of a divided by b in this order. So we want to take advantage of that property to rewrite this, and we're going to rewrite it as one big happy ln function. So the ln as h goes to 0 of ln of a plus h divided by a all over h. Okay, so we get to bring these two separate ln functions tucked under one big happy ln function. Okay, next I'm going to rewrite this to put it out in front as a factor. In fact, it is. So it's the limit as h goes to 0 of 1h times ln of, and then we have this a plus h all over a. So I'm going to go ahead and separate those two into two separate fractions. So I'm going to separate this into a over a plus h over a. Good. Now a over a is just going to be 1, so let's simplify that. Okay, and now we want to use another property of log functions. Another very useful property is that if we have ln of x to the power of p, for example, then this is equal to p times ln of x. So a number written exponential notation, in the argument of the log function, we can bring the exponent out in front and use it as a linear factor. Good, and that's what we want to do here, but in reverse, we want to bring this in here and raise it. Now, it's very important that all of this, everything in the argument of the ln function is going to be raised to this power. Okay, so let's write that. Okay, we're getting closer to what we want. So I just brought that up there. All of it is being raised to that power. Now I'm going to do one more little thing. I'm going to introduce an a over an a right here. A divided by a. It's just another version of 1. Hopefully we haven't really changed anything much. So we'll have f prime of a equals to the limit as h goes to 0 of ln of 1 plus h over a to the power of a over h times 1 over a. Okay, so let's move this out in front. So now I'm going to rewrite this one more time and say this is the limit as h goes to 0 of the limit of, and then I'm going to have to rewrite this as 1 plus h over a raised to the power of a over h. And now all of that is being raised to the power of 1 over a, right? Because multiplication can be rewritten this way. Okay, and the reason we do that is because now I can take this and move it out in front using the exact same property. Using this exact same property. So this becomes f prime of a equals to the limit as h goes to 0 of 1 over a times the limit of times ln of 1 plus h over a to the power of a over h. Okay, let me rewrite this up here. Okay, so now we can move this constant out in front because it has nothing to do with h. So let's rewrite that. F prime of a equals to 1 over a limit as h goes to 0 of ln of 1 plus h over a to the power of a over h. Okay, so what we're going to do is we're going to let a new variable come in. Let's let w equal to a over h. No. Let's let w equal to h over a, which means that if we flip this around, that means that 1 over w equals to a over h. Okay, so that means that this guy right here, we're going to rewrite that as a w, and this whole exponent is going to turn into 1 over w. Okay, so let's rewrite that. We have f prime, some space there. F prime of a is equal to 1 over a. I'll skip that limit for a second, and then we have ln of 1 plus, and then we'll have w raised to the power of, and then this is 1 divided by w. Right? Replacing the a over h by 1 over w, and replacing the h over a by w. Okay, well, we're allowed to do that, but we can't just copy down the limit as h goes to 0 because there's no more h's, right? We got rid of them, and we got rid of them by following this, right? We set this up. Let this be true. That's the conversion factor here. So we have to think about the limit. So as h was getting infinitely close to 0, the limit as h goes to 0, as h is going to 0, remember a is just some constant, so that would mean that if this numerator was going to 0 divided by some constant, that means that then so is w growing to 0. So this just turns into the limit as w goes to 0. Okay, well, when we were working with our functions, when we were working with limits, we learned that if we have a composition of functions, we can just bring it in here, figure out that answer, and as long as it was a value within the domain of the outer function, then we didn't break any math laws. And that's what we're going to do. We're going to bring this limit on the inside here, and as long as the resulting limit is in the domain of our outer function, we should be able to get a valid result. Okay, so now this is going to be f prime of a equals to 1 over a times ln of, and then I'm going to bring that limit on the inside, ln limit as w goes to 0 of 1 plus w to the power of 1 over w. And if we'll recall, that's exactly a definition of E, right? So if you recall, E has been presented as in a couple of different ways. So one of them is that it's equal to the limit as x goes to positive infinity of the function 1 plus 1 over x to the power of x, or equivalently, it's equal to the limit as x goes to 0 of 1 plus x to the power of 1 over x. Okay, so we have a couple of different ways in which we can express E, and that's clearly what this is right here. So we can establish that this whole thing here is equal to E. So coming back over here, we get that f prime of a equals to 1 over a times ln of e. And of course, ln of e is just equal to 1. Right? These two are inverse operations of each other. So this just becomes 1. And so f prime of a equals to 1 over a. Okay, what have we established? So given the function ln of x, its derivative is going to be equal to 1 over x. So given f of x equal to ln of x, its derivative at a f prime of a equals to 1 over a. Another way that that's presented, meaning the exact same thing, is just to say that if f of x is equal to ln of x, then f prime of x is just equal to 1 over x. Good. Or the derivative with respect to x of ln of x equals to 1 over x. Good. Okay. Hopefully that makes sense. Let's see. Okay, so given that f of x equals to 4x to the power of 3 minus 3 ln x plus 2e to the x power plus 7e to the second power plus 9x plus 2, find f prime of x, so find the derivative. All right, so let's see, f prime of x is equal to the derivative with respect to x of this whole thing, so let's copy it. 4x cubed minus 3 ln x plus 2 e to the x plus 7e squared plus 9x plus 2. Okay, so f prime of x is equal to, okay, I know I can break this down a little bit by separating the addition and subtraction of each term. So I can find the derivative of each one of these terms being added or subtracted, and I also know that I can bring out some constants, so I'm going to take a couple of steps, do a couple of steps in one. So 4 times the derivative with respect to x of x to the third power minus 3 times the derivative with respect to x of ln of x plus 2 times the derivative with respect to x of e to the x plus, and now this is the tricky one, there is no variable here. Even though it's written in the form that looks like it might be a function, e to the power of 2, that's just like writing square root of 3, for example. That's just a number, right? We just don't know how to write it exactly. It's an irrational number that goes on forever, so we can approximate it, we can use a calculator to approximate it, or we can just leave it like this to represent that number. Okay, so in that same way, e to the power of 2 is just some number. So this is just the derivative of a constant. It's going to be the derivative with respect to x of 7e to the second plus 9, the derivative with respect to x of x, plus the derivative with respect to x of 2. And this one is going to be 0, and this one is going to be 0, because we know the derivatives of constants is just equal to 0. Okay, so that simplifies that. So f prime of x is going to be equal to 4 times 3x to the power of 2 minus 3 times, and then we just discovered that the derivative of ln x is just 1 over x, plus 2 times e to the x, the derivative of e to the x is e to the x, plus 0, and then the derivative of x is just going to be equal to 1, so we just get a plus 9. Good, so we just simplify that a little bit. F prime of x equals to 12x squared minus 3 over x plus 2e to the x plus 9. And there's our final answer. Okay, so we've developed two important derivatives. If we have a function e to the x and we want to take its derivative, the derivative with respect to x of e to the x equals to e to the x. So we did a whole bunch of stuff to figure out the derivative with respect to. Also, we've established that the derivative with respect to x of the log function ln of x is equal to 1 over x. This is, of course, keeping in mind that the domain of the log function is values that are greater than 0. So this is for x being strictly greater than 0. Okay, so we have two very important, very useful derivatives. It was very painful to derive them. Don't worry, the derivation is not something you're responsible for, so I wouldn't put that on a test. I wouldn't say derive figure out how to prove that the derivative of e to the x is e to the x. I wouldn't do that to you. But hopefully it kind of made sense and you kind of understood it. But really the end goal is to figure out these two derivatives, and your homework will have a whole bunch of these here. Okay, but these are both unique examples of a much larger family of functions, as we saw before. If we just focus on the exponential family of functions, if we have, say, for example, f of x equals to b to the x power, this is where b is some constant. That's somewhere between 0 and 1, union with 1 to infinity, right? So it's some positive constant greater than 0, but also it can't be the number 1. And of all possible values of b, e is one of those values. It's somewhere between 2 and 3, right? It's 2.718-ish. So somewhere around here is e. Somewhere in there is one example of this value b. And same thing with this function. This is just one example of a larger family of functions. If we have some function g of x equal to log base b of x, right? Once again, the same b value, the same restrictions on b occur. And we know that if we have b equal to b equal to e, then we have the natural log function. Okay, so we have two very, very important derivatives, very useful. We use them all the time, but they are really just unique examples of a much larger, more general function. And so that's what we want to look at next, these more general functions. What's the derivative of just b to the x, where b is allowed to be any one of these values, not just e? Or what is the derivative of log base b of x, where b is allowed to be any one of these numbers, not just e? Okay, so that's what we're going to work on. I'm going to start with this guy here. Let's figure out this derivative. It would, by just looking at it, you'd think that that's the harder one, but actually it's not, because we can use some properties of logs to help us figure out what this is, and it's not so bad. Okay, so let's figure out the derivative of this more general function here. Okay, so given some function, let's call it f of x. F of x equals to log base b of x. Our goal is to find f prime of x, right? The derivative of this function. To do that, I'm going to begin by rewriting it as this. So f of x equals to log base b of x. I'm going to rewrite it as y, using y notation. So this is the same thing as y equals to log base b of x. And we're asked to find y prime, right? Different notation, same thing. Find y prime. Okay, so working with this, we know that our properties of logs, we know that it's going to be this base written to the power of that must be equal to this. So we can find an equivalent exponential statement, an equivalent statement written in exponential form to this. So we say that an equivalent statement would be to write b to the y power equals to x. B to the power of y equals to x. Keep in mind, we're still interested in this guy. This is what we want to know. Okay, so this is true by the very definition of of logs, right? This statement is true only if this statement is true, and this is just the exponential form. Right? Logarithmic form, the exponential form. One is true if the other is true. Okay, so now what we're going to do is we're going to take the natural log of both sides of the equal sign. So let me copy this down. We're going to do b to the y power equals to x, and we're going to introduce this ln. So we're going to take ln this side, ln of this side. Okay, we're going to use our properties of logs that if the index is the same, the argument of the ln function is the same, as we are told it's the same up here, then they both give you the same values, right? In other words, ln of a equals to ln of b. The only way this could be true is if and only if it's true that a equals to b. If then. If ln a equals to ln b, then it must be true that a must be equal to b, right? And we can go forwards and backwards. This allows us to apply the log function to both sides of the equal sign. Okay, now that we have that, then we can use our properties of logs. We can bring that exponent out in front. We know that's a very useful, very popular property of logs. So y times ln of b must be equal to ln of x. Good. Now I'm going to divide both sides by ln b, and we get that y equals to ln x over ln of b. Okay, so what we have here, if we want to focus our attention to this, y equals to log base b of x, and y also equals to ln x over ln b. So what we want to do is say that those things must be equal to each other, right? Since they both equal y, they both equal to each other. So I'm going to bring them together. And say that log base b of x must be equal to ln of x over ln of b. Right? And both of them equal to y. So now remember, our goal was to find the derivative of y. So we're going to take a derivative of both sides. This is saying we want this. We want the derivative with respect to x of this side. So we log base b of x. And doing this, well, this is y. So this is the derivative with respect to x of y. So taking the derivative of this side would be the same thing. Is equivalent to taking the derivative of this function, ln x over ln b. Okay, so now note that ln b is just some constant. This is the derivative with respect to x. B is some constant to be selected, and we know that b has to be a positive number, strictly greater than 0, but not allowed to be a 1. So let me write that down. Note, b is positive, strictly greater than 0, but also b cannot be equal to 1. Right? Another way of saying that is that b is a member of the set between 0 and 1, union 1 to infinity. They're both saying the same thing. Anyway, it's some constant to be selected. It's not the variable x. So we know from our work with derivatives that we can pull out that constant. So the derivative with respect to x of log base b of x equals to 1 over ln of b times the derivative with respect to x of ln of x. Okay, so 1 over b times the derivative with respect to x of ln x. And, well, this is a derivative we just figured out, right? So this is easy. That's just going to be 1 over x. So now we have that the derivative with respect to x of log base b of x is equal to 1 over ln of b times 1 over x. Okay, and that's the derivative we're after. Okay, so let's recap. We started it with this function, f of x equals to log base b of y, and we wanted to find its derivative. What's f prime of x? Okay, so I rewrote it using our notation, this notation, y equals instead of the function notation. So y equals to log base b of x. Same thing as that, we're trying to find y prime. Okay, so then we use some basic properties of logs. We can rewrite this as b to the y power equals to x. And then we're allowed to take the ln, apply both sides to the ln function. Okay, and then we get to move the y out in front, another property of logs. We move this around and we end up getting to a point where y equals to ln x over ln b. This is also called the change of base formula that you can do this. Okay. So now that we have that, we can take the derivative of both sides and we get to our answer. So bringing it all together, we could say that if we have f of x equal to log base b of x, then its derivative is going to be equal to 1 over ln of b times 1 over x. And this is, of course, only valid for x being strictly greater than 0. X being strictly greater than 0. Okay, so we found another very important derivative. We have 3 so far. We know the derivative of e to the x, we know the derivative of ln of x, and now in a more general form, we've established the derivative of log base b of x, where b is established here. I'll write it here again just to put it in a nice little box here. This is for b strictly greater than 0 and also b not equal to 1. Right? So as long as b is one of these values and x is strictly greater than 0, that's the domain of the log function, then its derivative is going to be equal to this, ln of b times 1 over x. And my ln looks funny. Let's fix that. ln b times 1 over x. Good. Okay, so that's a great function to have, but we had one other one that we wanted to work with, and that was a more general form of b to the power of x. So now if we have some function, let's call it g, we had some function g of x equal to b to the power of x. Again, the same restrictions on b. B has to be positive, but not 1. For b being greater than 0, but b not equaling to 1. Okay, so how do we find that derivative? To find this derivative, we're going to take advantage of a unique property of exponential numbers. We can always write any number in terms of an exponential one. So, for example, if you're thinking about 2 to the power of x, I can write any number in terms of 2 to the power of x. Obviously, if your little brother is turning 2, we can just say it's equal to 2 to the first power. But if your little brother is turning 8, we can say he's not turning 8, he's turning 2 to the power of 3, right? I mean, you could put this on his cake, happy 8th birthday or happy 2 to the 3rd power birthday, right? And so, of course, nice whole numbers work out really nicely. But, you know, when you turn 16, you get 2 to the power of 4. But what if you were turning 15? What do you do? Well, remember that 2 to the x power is continuous. Every single output is experienced that's positive, greater than 0. So you can always find some other number than the exponent here that might not be a whole number, might be a decimal, that equals that value. So, for example, let's find all of your birthdays, base 2. Well, let's just take a few examples. Let's look at Desmos. Okay, so here on Desmos, we have 2 to the power of x, and I create a little table here. So, of course, if you were turning 2, if you were 2 years old, I can say that you're 2 to the power of 1, okay? That one was easy. We also found that if you were turning 4, returning 4, you can say, okay, it's not really 4, it's 2 to the power of 2, and likewise 3, 2 to the power of 3 is 8. So you can say happy 8th birthday, or you can say happy 2 to the power of 3 birthday. Okay, and then of course we said, okay, well, what about if you're like 16? Of course, we can have 4 there, and there you go. Happy 2 to the power of 4 instead of 16. Okay, but what if it wasn't a number like this, a nice pretty whole number? Well, notice that that blue line is continuous. Every single value is experienced. It's just that the exponent on top of the 2 might not be a pretty whole number. It might be an ugly decimal. So for instance, I'm guessing many of you are in the neighborhood of 18. So let's look at 18 for y equals to 19. Okay, so if I establish the horizontal lines at y equals to 18, 19, 20, 21, the places where they cross, the intersect points, will give us the input value needed for 2 to the blank power to be equal to these numbers. I'm going to change the scale of this so we can have a better look at those. So let's go, looks like 5 is the biggest that needs to go along the horizontal. Go to graph settings. Let's go from negative. Okay, that looks a little better. All right, so now we have these nice, pretty whole numbers right there, right there, right there, right there. And then we have these more complicated decimals. And this is just an approximation, of course. So we have that. Okay, let me take a picture of this. Okay, so what each of these is saying is that, starting from here, this is saying that 2 to the power of 1 equals to 2. So you can put 2 to the power of 1 on your little brother's birthday cake, or you can put 2. You can also say from here, we can say that 2 to the power of 2 equals to 4. So again, you can put this on their cake, or you could say this number. Same thing with this one. 2 to the power of 3 equals to 8. Or this one, we can say 2 to the power of 4 equals to 16. Sweet 16th birthday, you could say sweet 2 to the power of 4th birthday. Sweet 2 to the power of 4th birthday. Right? Okay, and then, well, what if there weren't whole numbers like this? So I'm guessing many of you are in the age range of 18, 19, 20, 21, in that age range. So this is saying that if you're 18, you could say happy 18th birthday, or you can say happy 2 to the power of 4.17. Good. That should be the, what if you turn 18, you have the right to vote. There you go. 2 to the power of 4.17, the right to vote. 19, 2 to the power of 4.248. And of course, this is rounding. It's approximately equal to 19. There you go. 2 to the power of 4.248. That's your 19th birthday. 20, to that one, the 20th, that would be 2 to the power of 4.322. That equals to 20. And of course, the big one here in the US, 21, the right to drink. Right, so that would be 2 to the power of 4.392 equals 21. Right, so if a cop pulls you over and asks you, if you well, actually, that wouldn't work. Right, so in the US, the legal age to drink is 21. So if you want to get into a bar, you have to be 21 years old. There should be a sign at the door, must be 21 to enter. Or you can put a sign at the door, must be 2 to the power of 4.392 to enter. Right, if I ever open a bar, that's what I'm going to name it right here. Must be 2 to the power of 4.392 to enter. Yeah, it's going to be a very popular bar. Any rate, so you get the idea. any number can be written in terms of a power. Now, I just chose 2 arbitrarily. It could be anything. I could do the exact same thing with 3 to the power of x or e to the power of x or any power. We can always rewrite it in terms of anything. It's kind of like saying dozens, right? We like to use that word a lot in English. So dozen, usually in terms of eggs, dozen equals 12. But you can also say half dozen. Half dozen equals to 6. Or you can say 3 dozen. 3 dozen. Well, that's equal to 36 eggs, right? And in everyday conversation, we don't really use too many other variations on this. A dozen, 2 dozen, 3 dozen, half a dozen. But half a dozen, we can also think of that as a percentage. It's 50% of a dozen. So if you open up the floor to allowing percentage fractions of a dozen, then we could say I want 80% of a dozen. That's equal to some number, right? So there is some percentage that can be written in front of the dozen, and that could be equal to any number at all, right? So this is equal to 0.8 times 12. Is equal to 9.6. Okay, so you get the idea. All right, so if we could use 2, we can use any other exponential base. So why not use e? That's what we're going to do. We're going to use e. And remember that e is just going to go from here, and it's going to shoot up a little bit faster than this one, since this is base 2. So it's going to come up from here and go, kind of like that. And it's still going to intersect all of these numbers. They're going to be different places where they cross along the x-axis, but it's going to cross all of them. So you can write your ah base 2, or you can write it base e. Let's look at the one, just one of them. Let's look at the one for the 21. What if it was written base e, e to the x power? What would that be? Let's use Desmos. So if instead of base 2, we come over here and say, no, let's think about it as base e equals to e to the power of x. There it is. I had it in red. Let's match. Here it is. Here is base e, and notice that again it crosses the horizontal line that equals 21. So there it is. Come to think of it, maybe this would be a better name for a bar. Base e is more popular. So this is saying that e to the power of 3.045 is equal to 21. Okay, so that little intersect right there was 3.045, comma 21, indicating that e to the power of 3.045, that this is approximately equal to 21. So I think that would be an even better name for a bar. E to the power of 3.045. Any rate. Okay, so just pointing out that you can always do that, and we need to take advantage of that property in order to find the derivative we're interested in. So let's go back to where we were. Okay, back to here. We are interested in figuring out the derivative of b to the x power. So what we're going to do is we're going to write it in terms of e. As we just saw, for whatever number this is, we can always express it in terms of e to the power of some number. Okay, so let me erase this right here. So I'm going to rewrite this using y notation. So y equals to b to the x power. And you want to find, of course, y prime. You want to find the derivative of this. Okay, so what I want to do is apply the natural log function to both sides here. So I'm going to rewrite this as ln of y equals to ln of b to the x power. So we know from our properties of logs, I can move that exponent out in front. And so now ln of y equals to x ln of b. And now what I want to do is I want to raise e to the power of both of these. So I have e to the power of ln of y is equal to e to the power of x ln of b. Okay, and so now e raised to the power of ln y, we know that these two are inverse functions of each other, so they undo each other and they drop down to just say that that's equal to y. This left part is equal to y. So we have that y is equal to e to the power of x ln of b. Okay, so I want to point out, remember that b is going to be some value chosen in this domain of this function. So ln of b, this part here, is just going to be some constant, right? It might be 0.75 or something. It's some decimal value, some constant number to be determined. I don't know it, but I can treat it as a constant. So at this point, we've established that y equals to b to the x can be rewritten as y equals to e to the power of x ln of b. This is equivalent to what we were doing with Desmos. We're saying that when this number is given, once you choose b, I can say, you know what, I don't want to deal with b to the x power. I can rewrite it in terms of e. Any number presented in this form, b to the x power, can be rewritten as a number that is written base e, right? That's what this is establishing, right? Just like if you're 21 years old, you can always rewrite that number as a number base e, right? So if this is given, I can rewrite it like this. Okay, now as for the actual derivative, right? Okay, so we've established that y equals to b to the x can be rewritten as y equals to e to the power of x ln b. But what is that? What is that derivative? Well, our book has chosen to kind of do things in a kind of a strange order. In the next couple of sections, in section 3.4, we're going to visit something called the chain rule. And once we learn the chain rule, this will be a very easy derivative to figure out. But for now, if we don't have that chain rule, then it's just kind of a, trust me kind of situation, which I'm not a fan of, but that's what the book did. It said, okay, well, it can be shown, right? So wait until, 2 sections from now to figure out why this is. So it's unhappy, but I'm in a weird place because if I go through the trouble of showing the chain rule first, well, then, I'm going to be going out of order, and that might mess with you guys. So I will say in chapter 3.4, in section 3.4, we will learn that if we have e to the power of some constant x, right, where c is some constant, where c equals to any constant, and we want to find the derivative of that, the derivative with respect to x of e to the cx is equal to c times e to the cx, right? We will learn that in chapter 3.4. It's a simple pattern, right? If we have some constant in front of the x, then its derivative is just going to be to repeat the whole thing, including that constant, leave it up there, the whole thing, repeat it, times that constant that goes out in front. Okay, so in your book it just says, it can be shown that this is true. Yeah, it'll be shown in section 3.4. But for now, we're just going to go ahead and apply it here. And again, pointing out that ln b is just some constant. So that's like the role of c. So just using this from chapter 3.4, we can see that if we want to take the derivative of both sides, so the derivative with respect to x of this y is equal to the derivative with respect to x of this e to the x ln b. And so now this is going to be dy dx. Well, that's just exactly what we're interested in. Dy dx is then equal to ln b times e to the power of x ln b. So you just bring that constant out in front, and then you copy it. This is a multiplication, so I can fix this. I can rearrange this by bringing the x back up in the exponent. So dy dx, another notation style for it is that y prime equals to ln of b times e to the power of ln of b to the power of x. Right, so what I did is, using our properties of logs, I know I can move this up to the exponent inside the argument. So I moved this guy inside the log and moved it to the exponent, like that. And now these are inverse operations, so they will undo each other, and we get that y prime is equal to ln of b times b to the x power. Okay, so we figured out what we wanted. We found the derivative. Let's put it in a nice little box. So if some function g of x, let's put it over here, if some function g of x is given of the form b to the x power, for b being strictly greater than 0, but also b not being allowed to be 1. So if we're given that and we want to find the derivative, g prime of x, well, according to this whole work over here, it's equal to b to the x again times ln of b. So I'm just going to write it as b to the x power times ln of b. Good. Okay, so now we have the more general form, the derivative of the more general form. Okay, so we have 4 important derivatives, 2 very general ones like this, and then 2 of them that are based in e. Your book put them all in a nice pretty little box, so let's look at that. Okay, so here they are, all 4 of the derivatives we have found so far. So we start off with these 2. The derivative of e to the x equals to e to the x, and the derivative of ln x equals to 1 over x. Notice the conditions on b. B must be greater than 0, not equal to 1. And same thing down here, b must be greater than 0, not equal to 1. But also we add the condition that x must be strictly greater than 0, noting that you cannot plug in a negative into an ln function or to any log function. The domain is just positive numbers, so that's why we have to put that restriction there. Up here, the only log we're going to take of is log b, and well, we already have the restriction that b has to be positive, so no chance of b being a negative number, no chance of taking ln of a negative number here. That's why we don't have to put this extra condition here. Okay, but we just now discovered these more general forms. So e to the x, well, that's just one specific case of b to the x, where b happens to be e, but b could be anything at all. So the more general derivative is right here. Derivative with respect to x of b to the x equals to b to the x ln of b, and the derivative with respect to x of log base b of x equals to 1 over ln b times 1 over x. All right, let's look at an example that uses these. So let's see, for example, given that f of x equals to 5 to the power of x minus 2 to the power of x plus ln of plus 3 ln of x, minus log base 3 of x to the power of 2. Let's say we have this really ugly function here. So let's say we have this really ugly function here and we want to find the derivative. Okay, so that means we want to find f prime of x. F prime of x, which will be equal to the derivative with respect to x of this whole thing. So that'll be 5 to the power of x minus 2 to the power of x plus 3 ln x minus log base 3 of x squared. Okay, so whenever we have terms being separated by addition and subtraction, we know that we can separate them. So this is equivalent to the derivative with respect to x of just the 5 to the x power minus the derivative with respect to x of the 2 to the x power plus the derivative with respect to x. And I'm already going to skip this part here and put it out in front. We know it's a constant. It's going to be 3 times the derivative with respect to x of the ln of x minus the derivative with respect to x of log base 3 of x squared. Right, so we can separate them into individual little pieces. Okay, so this is going to be a straightforward application of our logs. So will this, but not this one. Notice that this one's a little bit different. Log base 3 of x squared, well, we don't have anything on here where the argument is being raised to an exponent. It's similar to this one. It looks a lot like this, where the b is a 3, but we don't have anything about an x squared, right? So what we have to do is, first of all, use one of our properties to simplify this. Let's put that 2 out in front. And then we know that when there's a 2 out there, we could put it out in front as a constant. Okay, so let me recopy this. d dx of 5 to the x minus d dx of 2 to the x plus 3 d dx of ln of x minus, and I'm going to pull the 2 out in front, and then that's just some constant, so I'm going to pull it out in front here. Say that that's 2 times the derivative with respect to x of log base 3 of x. So now it'll look just like this one. Okay, so let's name them here. So this is a 1, a 2, a 3, and a 4. So I can reference them here. So this one, this derivative is going to be like a number 2, right? You go to McDonald's and you order something, give me a number 2. This is going to be a number 2 where b equals to 5, right? Just like that one, b to the 5th. This one's also going to be a number 2. This is where b equals to 2. Oh, there weren't any number 1s. Okay, well, interesting. This one's going to be like a number 3, right? Exactly like it. This is the number 3 here. And the number 3. And this one is going to be like 4, just like a number 4. Give me a number 4, and this is where b equals to 3. b equals to 3. Okay, so let's apply them. So this is going to be like a number 2. So the derivative is going to be equal to copying that same thing again. So 5 to the x times ln of b. So this is going to be 5 to the x power times ln of 5 minus 2 to the x power ln of 2 plus 3 times, and this is like a number 3, derivative of ln x is equal to 1 over x, minus 2 times, and this is like a number 4. This is going to be equal to 1 over ln of 3 times 1 over x. So 1 over ln of 3 times 1 over x. Okay, so we can maybe simplify this just a little bit, but not much. F prime of x, f prime of x, f prime of x. Just going to move it up here just to have some more space. So given f of x, the original function, is equal to 5 to the x power minus 2 to the x power plus 3 ln of x minus log base 3 of x squared, then we just discovered that its derivative is going to be equal to 5 to the x power ln of 5 minus 2 to the x power ln of 2, plus, and I'll just rewrite that as 3 over x, minus, and that's going to be 2 over x ln of 3. Right, just combining all of this into one big happy fraction with the 2 in the numerator and then the product of these two in the denominator. Okay? All right, let's look at another example. Okay, let's take a look at this word problem. A model for the growth of a sandwich shop franchise is given by n of t. N of t equals to negative 765 plus 482 ln of t, where n of t is the number of locations in year t, where t equals to 0 corresponds to the year 1980. Okay, let's explore this, this equation a little bit so we can create a table of values, come up with a few key values, and see how this interprets. Let's use Desmos. Okay, so on Desmos, I put in the equation right here in this little table, negative 765 plus 482 ln x. So we can find a few key values. So let's say when x is equal to 1, we end up with negative 765. Let's see what that means over here. So if, let's put a little table here. So note that if we have t equal to 1, then we have n of 1 equals to negative 765 plus 482 ln of blank. So if we're putting in a 1 there, and a 1 there, ln of 1 we know to be 0. So that means that this whole thing becomes 0. And so we get n of 1 equals to negative 765. Okay, so t equals to 1 means that it is 1 year after 1980, right? T equals to 0 corresponds to the year 1980. So this is saying in 1981, there were negative 765 shops. Okay, that doesn't make any sense. Remember that a mathematical equation is just approximating a real-world situation, but there are limits to that. So clearly, this equation is not really making sense for the case of t equals to 1. And it also doesn't make sense for the case of t equals to 0, obviously, because if we have t equals to 0, we end up with the equation n of 0, n of blank equals to negative 765 plus 482 ln of blank. And so here will be 0 there and 0 there. And we know that ln of 0 is undefined, right? 0 is not in the domain of this function. So this whole thing is just does not exist. It's undefined. So it doesn't make sense for 0. Okay, that's fine. It will eventually make sense. We're told that this equation does a good job of approximating the number of shops. It's just that there's a segment of the domain for which this is valid. And clearly these two numbers are not in it. Okay, so let's keep going until we have more realistic answers, and let's use Desmos. So if we try and put in a 0, we're going to get an error, undefined. Okay, that's fine. What about 2? This would be 1982, still negative. 3, still negative. 4, still negative. 5, still negative. Oh, okay, finally, 5. 5, we have a positive number. So when we plug in 5 into our function, ln of 5 times 482 plus negative 765, we finally have a positive answer, which starts to make a little bit more sense. So here we have this point there. So let's do a few more. How about 6, 7, 8? Okay, I'm going out of control here. Oh, wow, it's growing really quickly now. So now year 5 corresponds to 1985. There were 10. 1 year later, there's about 98 of them. 1 year after that, 1987, now there's 172 of them. By 1988, there's 237 of them. So I have to zoom way out to find them. So here's the ones we found so far. So it looks like this is growing pretty quickly. Okay, all right. But this specific question said, estimate the number of locations in the year 2028 and interpret your results. So the year 2028, for part A, let's answer part A. The year 2028 corresponds to a t-value of 48. Remember, t is the number of years since 1980. So if you were born in 1980, in the year 2028, you'll be 48 years old, 48 years later. Okay, so all we have to do is evaluate this function at 48. Negative 765 plus 482 ln of blank. So we're going to put in a 48, ln of 48. Put it in there, and now we just have to use our calculator. So let's get our calculator out. And we want to calculate this. So I'm going to start off with ln of 48. ln 48, close parentheses, get an answer. Multiply that answer by 482. Get an answer, and then we want to subtract 765 to get approximately 1100, 1100.9189. Okay, so remember, this is this function is approximating the real world, so there wouldn't be 1,100.9189 shops open. It's going to be something close to that, so we can round. So we can say that based on our approximation, we estimate according to our model, in the year 2028, we estimate that there will be about 1,101 shops open, approximately. Okay, and then for part B, estimate the rate of change in the number of locations. How are those changing in that year? How is the growth? What is the growth happening in that year? So we know we need a derivative. We know we're going to need the derivative. So we have n of t equal to negative 765 plus 482 ln of t. Let me zoom in here. And I know I'm going to want that derivative, so I'm going to do that n prime of t is equal to the derivative with respect to the variable t, right? Normally we have x, but now we have the variable t of this function, negative 765 plus 482 ln of t. Okay, so we know we can separate these, so this will become the derivative with respect to t of 765, negative 765, plus 482 times the derivative with respect to t of ln of t. Okay, well, we know that this derivative is going to be 0. It's the derivative of constant. And we know that the derivative of ln of t is just going to be 1 over t. So that makes life easier. Get n prime of t equals to 0. And then this will just become 482 times 1 over t. So we can just simplify that as just 482 divided by t is the derivative. Okay. And so this was when t was equal to 48. Here. When, or I should say, when t equals to 48, then n prime of t is just going to be equal to 482 over 48. So when t equals to 48, then we'll have 48 there and a 48 there. Divide those. You get pretty close to 10. Right? Let's see. 482 divided by 48, 10.04. Or approximately 10. So, this is the derivative at 48. So what this is saying is that the rate of growth in the year 2028 is approximately 10 stores per year. Rate of growth. The instantaneous rate of growth at that year, rate of growth is about 10 stores per year. So that's approximately how many stores we can expect that they'll open that year, 10 additional stores. Okay, so now we can kind of piece it all together and say, if this is the equation that describes the number of locations as a function of t, where t is the number of years since 1980, we found a couple of interesting ones here, but we can see that the function, that this model does not apply for these years. But we were asked about the year 2028. In the year 2028, t is equal to 48. So if we plug in a 48 into there, we get approximately this number. So we can say that according to my model, in the year 2028, we estimate that there will be about a total of 1,101 shops open. And furthermore, we can say that in that year, we expect that they will open an additional 10. It's growing, right? I'll just put that over here to kind of continue on to this statement. And the franchise at this point, right? In the year 2028, we expect they're going to open an additional 10 shops. They're growing at a rate of 10 shops per year at that point. Okay, so here is what your author wrote as a solution. Same thing. It looks a little neater. So the year 2028 corresponds to t equals to 48. So we just plug in a 48 into our equation, get our calculator. It gives you about 1,101. So there will be approximately 1,101 locations in the year 2028. And then for part B, we took the derivative, same thing, plugged in a 48, which corresponds to the year 2028. Divide, and we get approximately 10. So the number of locations is growing at a rate of 10 per year in the year 2028. Okay, so remember, it's not a constant rate. It's not like they open 10 every single year, every single year. That would be a constant rate. The rate at which they are opening, the number of new stores that they open each year changes. And so in this particular year, they're growing at a rate of about 10 per year. The next year, they might grow at a slightly higher number. Okay, so That should be enough to tackle your homework. So go ahead and work on your homework and stop by my office hours if you have any questions.